that. Make sure that it's, yep, it's picking up my microphone. This is good news. And we're going to share this screen. There we go. So you should see the PowerPoints and such. We good? All right. Then what do we have left? What do we have to talk about? How to set up models. That's where I want to go with this. So I'm scrolling through the stuff we already talked about. Setting up the R matrix is the new part in introducing multivariate models. But changing how we specify the fixed effects is also potentially something that you need to worry about. And where do I want to go? I want to be here. Slide 24. Okay. So if you've taken design of experiments with REL, some of this may sound familiar to you, and if not, then this will be your first introduction to models that have more than one intercept. So I mentioned this back at the very beginning of the semester. You'll get a chance to practice this on your next homework. And this is an idea of trying to fit a multivariate model so that each outcome has its own linear model simultaneously, which is a more intuitive way of setting up the model when you have each outcome that stands alone. So what do I mean by that? In the last example that we did, example 4A, sorry, I've been working on 5A at home. 4A, the one that we just did, had 4 repeated measures conditions for response time. Do you remember that? So when in thinking about that, like the outcome is response time, and I observed it under 4 conditions. And so the way that I think about it is not really so much 4 outcomes as one outcome that I have predictors of which condition it's in. In the example that we're going to do today, I have responses from families, and each family has 3 responses from the dad, the mom, and from one of their adult children. So that's not the same as response time as like one thing, because you might want to know what predicts how the dad answers, what predicts how the mom answers, what predicts how they might disagree, like those kinds of things. And so when you're fitting a model where you want to know if, say, it's called actor-partner. Have you guys heard that terminology before? No? So it's a phrasing that lends itself to, say, dyadic data. Let's say that you have people in a relationship take a survey about how happy they are in the relationship and how often they feel they provide their partner with support. Okay, let's say that we have those kinds of variables. So what you might want to know is, if I feel like I provide my partner with support, am I happy? Are they happy? If my partner thinks they provide me with support, am I happy? Are they happy? Right? So if my predictor predicts my outcome, that's called an actor effect. If my predictor predicts their outcome, that's called a partner effect. So in those sorts of situations, where you're thinking of your outcomes as separate things because they're from separate people or otherwise, the version of the model that I'm about to show you is going to be more potentially useful and intuitive than what we did last time. Okay, with me? All right, so slide 24 here. So generic language here to start with, and then I'll show you a specific example that follows along with this. So let's say that I have 3 outcome variables. I want to predict all 3 outcome variables simultaneously. One is outcome A, other is B, another is C. So in preparing my data set for analysis, I would have which DV is which. So we're talking about a stacked data set where I've already taken the 3 outcomes and put them into one column. And I have an index variable as to which outcome goes with which row. So I would have a variable in my data set called DV that would be treated as categorical. It could be literally either a string or numbers that have value labels assigned so that what shows up on the output is A, B, and C. So that's one column. Additionally, then I would need to make 3 dummy codes. So I have an index for whether or not it's DVA, and if it is the row is for DVA, then that index takes a value of 1. If that row is not for if it's for B or C, that index is 0. If it is for B, then the index for B is turned on. If it is for C, the index for C is turned on. So this is a dummy-coded version of this index variable. It seems like it might be redundant, but it's not. They're going to act as filters that allow you to specify predictors for each outcome separately. Have you guys seen anything like this before in other models or other classes where you have more than one intercept in a model? Can you hear me? Not that you can recall. Okay, thank you, Kelly. Everyone else looks puzzled. And so that means they're thinking, or they can't hear me because my internet has crapped out. I used it in the previous example. Yes, just thinking. Okay, that's okay. Thinking is fine. Can hear you. Good. Okay. So these dummy codes right here, these are going to act like switches. That's what their job is. They're going to turn effects on when relevant for that column, or that row, or off. So in this configuration right here, there are 2 different ways to set up the model. There's the general intercept way. That's what we did in example 4a. And in that case, what you would do is designate one outcome variable as the reference. So in example 4a, the response time for the low-low combination was the reference outcome. And then we had the dummy codes for meaning and salience that differentiated that reference outcome from each of the others. That's the general intercept. So any effect that's for a non-reference DV under that parameterization would have to be found as a linear combination through an estimate statement or a lincom. The alternative that I want to show you today is a DV-specific intercept parameterization, multiple intercepts. That provides effects separately for each DV, and if you want to know if the effects differ between DVs, you have to ask for that as a linear combination instead. So it gets tricky to figure out what the hell your model means. So if you put which DV is which, that column, into the categorical option in your software, so if it goes on the class statement in SAS, or if it's an I dot or what's known as a factor variable in Stata or R, this is what it's doing for you internally. It's the exact same thing as what was on the previous slide, making these DV-specific dummy codes. It does it internally. You don't have access to those variables, but it wants to know what values would apply to each one. So if you put this DV variable on the class statement or put it as an I dot predictor in Stata, internally it's making those same sorts of DV dummy-coded variables. Is it A? Is it B? Is it C? If you have a general intercept in the model, which is what we've had always up to this point, it's going to leave out one of those columns and put the others in. Which one it leaves out is software specific. SAS leaves out the highest, the last one, that would leave out the is C. It's the highest numerically or the last alphabetically, and so that becomes the reference. Stata leaves out the first by default, and you can change it much more easily in Stata, which is why when I show examples with the class statement, I usually change it in Stata to be the last so that it matches the output in SAS. And so it figures out then how many contrasts are needed to differentiate the levels of this variable. If you're using an intercept, it leaves one out. If you're not using an intercept, it puts them all in. every time that you refer to this variable, predictor variable, in code, like in an estimate statement or a lincom statement, you have to tell it what to do with these values. And so let me show you what this is going to look like in an example, but just to set the stage for it. So here is what a general intercept parameterization looks like. When you leave in the general intercept, this is what we did in example 4a. So the notation here, y hat for an individual and then d for which dv it is. So y hat means the predicted outcome. So I have beta 0, I have beta 1 times the dummy code for dva, and beta 02 times the dummy code for dvb. So what that means is that the reference dv is for dvc. So beta 0 takes on the interpretation of the intercept for dvc. Beta 01 is then the intercept difference of c versus a, where c is the reference. Beta 2 is the intercept difference for b relative to c. Then you can get the differences between the non-reference groups, or dv's in this case, as the difference between the slopes, and you can get what the intercept would be for each dv as a linear combination. So the model directly gives you what the intercept is for one of the dv's and how that intercept differs for each of the others. If you add in a predictor, same pattern. Let's say I have my predictor x. I put in a main effect of the predictor. I put in an interaction of x with dva and an interaction of x with dvb. Well, that means the main effect is going to be the effect of my x predictor specifically for c, because that's when the other terms go to 0. Beta 1 is the difference in the effect of x for a relative to c. Beta 2 is the difference in the effect of x for b relative to c. And I can get the remaining difference as a linear combination, and then 2 linear combinations for what the slope is for each one. So this is the setup that you're used to, where there's one intercept and everything else that enters the model is some kind of difference relative to that anchor reference group, or reference dv in this case. So here's what the code would look like to do this. So if I have my 3 dv's in SAS or in Stata here, look at this. I have dva, dvb, the main effect of x, and the effect of x multiplied by dva and dvb. On the repeated line is the categorical index for dv. So these dummy codes are being treated as continuous by the model. They're being treated as quantitative predictors. dv is being treated as a categorical index. So anything that you put on the repeated line here has to go on the class statement. They have to go together or it will yell at you. In Stata, I'm doing the same thing. Residuals is where you tell it how to put your R matrix. So dv goes in there as an index. And in the model, I've got my dummy codes for a and b, x, and the interaction of x with those. If I wanted to use the dv variable as a categorical predictor too, not use the dummy codes, it would look like this. So it's the exact same model, just a different version of the syntax. If I put in dv and I have my general intercept, what SAS is going to do behind the scenes is put in its internal variables that it made that do the same thing as my external variables, dva and dvb. It does the same thing here for the interaction term. I can type one thing, dv by x, and it puts in these 2 terms that are implied by it, the interaction of x with each of the dv's. And same thing here in Stata. If you use I dot for dv, that's the analog of putting it on the class statement. Okay. With me so far? So when this version of the model, the version that you're most used to, this makes sense when you have one thing, one group, or one outcome, and you want to know if it differs under different conditions or for different people. This makes less sense if what you're thinking of is multiple outcomes. Like, I want to predict what the dad says. I want to predict what the mom says, because everything in these models is phrased as differences. You don't get to know what the dad says directly unless he's the reference DV. Everything else would be how the dad differs from the mom, it differs from the kid, that kind of thing. So let's take out the general intercept and fix it. So this is slide 28. This is your first instance of a model that has more than one intercept. The parts that make it different in terms of what goes into the model and what would go into the syntax are underlined. The difference here is that beta 0, what used to be the general intercept, now is multiplied by DVC. And the same thing is true down here for what used to be the main effect of X. It's multiplied by DVC. You would then tell the software to take out the intercept that it automatically puts in. There's an option called no int in SAS or no constant in Stata. These all become your intercepts. So beta 0 is turned on, so to speak, when the row that you're predicting has DVC equal 1. If it's any other DV, then this term, this term is gone. And likewise for these. So these DV-specific dummy codes act like switches. So beta 0 is turned on, is a set of ones anytime you're talking about C. So it's a C-specific intercept. Beta 01 is turned on anytime you're talking about A. So it's an A-specific intercept. And beta 2 is turned on if you're talking about B, so it's a B-specific intercept. So you have 3 intercepts in this model. And you can get the differences between them as linear combinations. If you add X, note in this equation there is no main effect of X anymore. It does not show up all by itself, because it would be ambiguous what it refers to. So these switches have to be attached to the effect of every predictor. It looks like an interaction term, but it's not. It's a nested effect. This is beta 10 is the effect of X specifically in predicting C. Beta 11 is the effect of X specifically in predicting A. And 12 is the effect of X in predicting B. So each of my 3 outcomes at this point has its own intercept. It has its own slope for X. But I'm doing all 3 simultaneously. That way I can ask for contrasts among what the intercept is for each outcome and among what the slopes are across for each outcome. Okay. Does that make sense, conceptually at least? So it's like 3 regressions at the same time. The dummy codes act like filters or switches to keep each effect separate. The reason to do this is so that you can compare, like, is the effect of X bigger for DVA than B? Is the expected value for A different than the expected value for B? It's to be able to make comparisons across these equations is why you do it simultaneously, but each outcome is predicted by its own linear model at this point. What it looks like in code. There's a magical thing here I've underlined. It's no int is a new option in SAS that goes after the slash on the model line, and the analog is no constant in Stata. That shuts off the column of ones that is normally added as a predictor by default. And so then you put in all 3 dummy codes, all 3 dummy codes multiplied by X. Same thing down here in Stata. If that's too much typing for you, then you can use the categorical syntax to let it make the dummy codes for you. And so if I type DV with no intercept, That's the same thing as getting a separate intercept for each dv. dv by x gives me the effect of x for each dv, because it understands that when I say dv, I mean the 3 internal columns of dummy codes that it made for me. And the same thing can be true in Stata. Okay. The automatically in these programs, the fixed intercept is added to the model. The no int and the no constant takes it out. And if you were to conceptualize what an intercept means as a predictor, it is just a column of ones. And so it takes out that column from the predictive equation, and it puts in these 3 columns that have ones and zeros strategically to serve to turn on which row the prediction should apply to. Sure. So I'm going to show you examples of this, and you'll see it with numbers. But just beware that it's easy to get this confused. You are allowed to mix and match across these 2 methods. No, it thinks I'm streaming. Okay, well that's good. All right, I'm back. Hooray. So let's say that you want to have one predictor that predicts all 3 outcomes, and a second predictor that only predicts A and B. You could do that. So if you fit the general intercept version, it would look like this. So you would have beta 0 not multiplied by anything, so it's 1 for everybody. You would have A and B, so that would be the difference between C and A and C and B. You'd have a main effect of x1, that would be for C, and then this set of betas here, beta 1, 1, and 1, 2, would allow that effect of x1 to differ for A and for B. But then we get to the bottom part here. There's no main effect of x2. So beta 2, 1 and beta 2, 2, even though they look like they should be doing the same thing to the equation above, they're not. Beta 2, 1 is the effect of x2 on A, not how the effect of x2 differs for A. And beta 2, 2 would be the effect of x2 on B, not how it differs, because it's missing that reference thing here. So this general intercept version is like a hodgepodge, because the first part of it is in reference to the intercepts. So there's an intercept plus and then differences. The second part here is more like the bottom. So we can get, you can have only some predictors predict some outcomes. You just have to be very careful in how you set it up. That's sort of the moral of the story. All right. Do you want to see what it looks like? Why not? Make this a little bit more concrete. All right, so we're still in normal lands for now. This is example 4B. These are real data, so that's why you don't have them in your folder when you download example 4B. They came from a study at Penn State University. So when I was at Penn State, I was a postdoc there, technically in the Gerontology Center, but when they let me start teaching, I taught in the Human Development and Family Studies Center. And so all the students there had family-type data sets, and so they were very excited to learn about multivariate models. It was multivariate, multi-level, actually, but we can do it for just single-level data for this. So this example has the outcome variable is gender attitudes about marriage. It's, I think, 5 items. I'm taking the mean across items on a scale of 1 to 4, where higher values mean that you have a much more conservative opinion about the role of a woman versus a man in marriage. So, you guys still there? Everyone looks frozen. Okay, yeah, you're just sitting very still. You're not frozen. Okay, good. Good. So I have this question, this set of questions, this outcome, I'll just say it that way, from These are adult children and their parents. So one child per family, the mom and the dad. And for simplicity, I selected it so that the data are complete, but you don't have to have a response from each person in the family to be included. The predictors that we're looking at, there's just two. One is the gender of the adult child. The gender of each parent is assumed because we have moms and dads, and so this is in simple binary gender land. And also the level of education in years of each person, thinking that people who are more educated may have less conservative attitudes potentially. So I did some preliminary looking at distributions and such, and it looked like normal was plausible enough, even though this is a scale score that has a floor and a ceiling. So I went ahead with that. So the first half of this is the first of two handouts that are going to have this structure. There's a part 1 and a part 2. I'm going to show you how to do all of these multivariate models using Stata and SAS in the way that you're accustomed. And then I'm going to show you how to do it as a path model, the exact same models. So the part 1 is the software. So we have to start out by taking a data set in which one row is for a family. So I've got the gender of the child as a variable, the education level of each person as 3 more variables, and then the marital attitudes variables as the last 3. And I need to take this wide data set and stack it so that it's 1 row per person rather than 1 row per family. So I have code for that below, but after we're done stacking, this is what we're going to have. We have 3 rows per family. All of the original predictors have been continued, so pasted down across the values. I have a new categorical index for which DV is which, and I applied labels to that, so kid, mom, or dad. I have my 3 dummy codes as to which DV is which, whether it's the kid, the mom, or the dad. And then I have marital attitudes, and it looks like this version of the data set had education, although I think I took that out, so I'll have to fix this picture yet again. But this is the column that we're going to be predicting. These are the predictors we're going to do it with, the dummy codes, and then education centered at 12 as well. This looks really big. Okay. All right, with me so far. So the code. So in the original data that I started with, the names of the variables to be stacked did not have numeric suffixes. And that made Stata very angry with me. So I had to recode them. So I had kid marital, mom marital, and dad marital. The first thing that I had to do was rename them to have numeric suffixes, because that is insisted on Stata and to use the reshape command. Once I did that, then they all go into a single column called marital. The 1 versus 2 versus 3, that information was saved into a new column called DV. I then took that variable and made a labeling system for it so that it says 1 kid, 2 mom, and 3 dad. That way I don't have to remember which is which, and it helps the output look a little bit easier to read. I then generated the dummy codes, and I know there's faster ways to do this in Stata, but I like this way because it's more transparent as to what you're doing. So setting each variable to 0 and then changing it to 1 if it's that particular DV. So any questions on the Stata setup for this? Stacking, making variables? No questions on from the Stata folks? Okay. SAS folks, 3 lines for my 3 different people. So I'm creating the categorical index and each of the dummy codes myself in the stacking thing. The single marital column is being created here. Output means write a new line of data. And I dropped the original outcomes that I no longer needed as well. So now we're ready to rock and roll. In this example, I'm not going to worry about the R matrix. I'm just going to let it be unstructured. there's only 3 outcomes, and so that's not that many extra parameters. So there's 3 possible covariances and 3 variances. I'm just going to leave them alone and let them be estimated. And we'll focus on the model for the means. So here is your first example of fitting a model that has DV-specific intercepts. So we're taking out the general intercept column of 1s, and we are putting in 3 dummy codes that give a custom intercept to each outcome. So in Stata, the magic happens right here. There is a comma after the predictors that then launches it into options. No constant is the option to remove the general intercept. Here are some extra pieces of output that I'm asking for. So the test statement here is asking if there are intercept differences across my 3 people. So in other words, are some types of family members more conservative in their attitudes than others? Are the dads different on average than the moms, or different on average than the kids? And so the way that I'm doing that is setting one intercept equal to another. And because there's 3 groups in total, I need 2 of these constraints. So this is going to give me an F-test for mixed, which is what we're using, which is for multivariate with this option here. DF method is Satterthwaite. You can pick from a couple different options. That's the one that I default to. And then this asks to put them in there. The small then carries that use of denominator degrees of freedom into the subsequent test or lincom. So I have screwed this up more times than I care to admit, but this is one of the dumbest things they could ever do. This drives me nuts. Because if you don't write small every single time, it's going to use a z or a chi-square instead of a t or an f. And so the results are logically inconsistent with what the model gave you, because the model is using denominator degrees of freedom and these statements aren't. So you have to write small every single time. I'm hoping in later versions of Stata they'll clean this up, but at least in 14, which is the one that I have at home, that's the way it has to be. So here's my 3 intercepts. Take out the constant. Here is the exact same thing using DV as categorical instead. So my 3 dummy code variables that I created are being replaced with the internal variables that Stata created for me by invoking this i.dot command. So instead of referring to the dummy codes, I now refer to those internal variables. And so 1.dv is the same thing as kid, because kid was number 1. 2.dv is the same thing as mom, who was number 2. And 3 is dad. So you can see the parallel more directly with the lincoms here. So the dummy codes are doing explicitly what Stata does internally if you use the i.dot. Does that make sense? Okay. Now there are reasons to do it the long way, and I'll show you why in, I would say about 10 minutes, but probably longer than that. Here's SAS. Same thing. Here's my 3 dummy codes. The magical no int option that shuts off the general intercept. Contrast is the same thing as test. So I'm contrasting, here's one pairwise difference and here's another. The comma separates multiple degrees of freedom for the test, so this is a 2-degree of freedom contrast. And the estimate statements then give me pairwise comparisons between the intercepts for each type of person. I can either type out my own explicit dummy codes that I made, or let SAS do it internally for me through DV. And so every time you refer to DV in a contrast statement or an estimate statement, you have to tell it what to do with each of its internal dummy codes. So DV -101, that's kid versus dad. -11, that's kid versus mom. This one is kid versus mom, this is kid versus dad, and this is mom versus dad. And how do I know which is which? It's the order in the data. So DV currently has a labeling system. Did I not? I don't think I pasted it in here. Oh yeah, I did. A labeling system that I did by cheating. I made it a string variable. So when I put DV on the class statement, the highest alphabetically is the reference if I have a general intercept. Otherwise, they go in the order in which DV is in here. So 1, 2, 3 is kid, mom, dad because that's what it is in the DV variable as I set it up. So that means when I refer to it, the order of the values is kid, mom, dad. Okay. Let's look at the output from just that much before looking at the other options of the models. So I'm showing you 4 ways to set up the exact same model, just an empty model. Because it's the same model, the R matrix and the log likelihood and everything will be the same. So I pasted in here a table. This is the R matrix. So variance on the diagonal for each person. So that we know that the first one is for kids, the moms, stop it, are second, and the dads are the third. Here's the R correlation matrix. So this tells us, without controlling for anything, how related the attitudes are of people from the same family. So kids and moms are correlated about 0.13, kids and dads are correlated 0.25, and moms and dads are correlated 0.29. So that would be something typically of interest in these sorts of studies. The contrast statement for whether there are any differences as a function of which person it is, 2 degrees of freedom, is the same anyway. But here's where the solution for fixed effects, what it would look like under each method. So if I shut off the general intercept and I put in my 3 dummy codes that I created myself, here's what I get. And these terms are readily interpretable, in my opinion. They're the intercept for each person. So there's no general intercept as part of my model. And this out here, by the way, is me being nice to you guys. SAS did not do that for you. Likewise, if you put in DV and let SAS do the dummy coding internally, what you get back is a list of each of these internal variables, and the estimates are the same. The lincoms are estimate statements for the differences between them. Kid versus mom, kid versus dad. Those turn out to be the same either way. Okay. So that's the new way of doing things where it tells you what the intercept is per DV directly. If you want to know if they're different, you have to ask for that as linear combinations. Here is the old way of doing it, the general intercept version. And by old, I mean the way you already knew, not that it's necessarily older, where we use the general column of ones, and that means we only put in 2 of the dummy codes. And I'm making dad the reference DV, and kid and mom are the other 2 dummy codes. So now in Stata, I've only got 2 dummy codes because the no constant that took out the fixed intercept is no longer here. Point of order, let me back up just 1 second because this is confusing as hell. Do you see this right here that I highlighted? No constant shows up twice. It is not redundant. I know, right? See, all of this intricate knowledge of code, this is job security, my friends. You develop this intricate knowledge of code, and I don't care what happens to the economy, someone will pay you because they don't want to have to learn this. I guarantee it. But the first no constant takes out the fixed intercept. That's the column of ones that we've been talking about today. The second no constant shows up after this bar thing. That takes out the default random intercept that Stata wants you to have when you tell it that you have an upper level sampling structure. So Stata understands that I have 3 rows per family, and it wants to put in an extra term that we haven't talked about yet called a random intercept to model the correlation between family members. Rather than doing that, I put it in the R matrix instead, so I don't need the random intercept. So this is the one that controls the fixed intercept. That will come in and out as I show you different ways of doing the model. This is the one that controls the random intercept. That one will always stay because there's not a random intercept in any of the models today. There will be next week, but not today. Stata and SAS differ in that SAS does not put a random intercept in by default, so I don't have to go to the trouble to shut it off. Only Stata does that. Okay, so back to the general intercept version. The first no constant is gone, so the general constant is back. That changes the interpretation of what those dummy codes mean. Same thing here by putting in DV. Same thing here in SAS. The no int is gone, or the DV here with the no int gone. So let me show you what happens in terms of the output. So the previous model that did not have a general intercept gave me the intercept per person instead. Cool. You use a general intercept. This is what it looks like. Like this one right here. So intercept, that's a column of ones. That's for everybody. The intercept, by definition, expected outcome when your predictors are 0. In this context, that occurs when we're talking about the DAD outcome. So the DADs are my reference outcome. They have the 1.95. So that matches what we got up above. Okay. So those two numbers are telling me the same thing. The DAD's intercept is supposed to be 1.95. Let me see. Yeah, I think I can. Yeah, you can see both the numbers at the same time. Now up here, kid and mom, relative to down here, kid and mom, they're not the same. So even though it's the same predictor variables in the model, it's just the 2 dummy codes for the kid and for the mom, they don't mean the same thing. Up above, without a general intercept, they represent the intercept for each DV directly. Down below, they are how the intercept differs for that other non-reference outcome. So what these numbers down here are telling you is that the intercept for the kid is lower than the intercept for the dad. And this number is telling you that the intercept for the mom is lower than the intercept for the dad. To get to what the intercept would then be for these non-reference groups, that's a lincom to add them back together. And so that's what the extra code that I wrote does to get them back. Same thing if you have a categorical. The intercept is for the reference group. That's the highest by default in SAS, and I made it that way in Stata so that it would match. And then stop it. The internal dummy codes give me the differences. Okay. So this is confusing as hell, right? Maybe. I think so. Question from Kelly. The reasoning behind using either one will be driven by the research question. Absolutely. So these things are mathematically equivalent to each other. You can get from one to the other is what predicts the outcome for each DV. Oh, frozen. Pausing. Am I back? Now I'm back. Okay, I think you are back. I'm back. Okay. Yes, I assume that from the Frozen comment is that I'm frozen, not that you wanted to hear the songs from Frozen. Let it go, let it go. No, not today. Thank goodness my son does not want to watch that movie. I've never actually seen it. I'm going to keep it that way if I can. But no, Frozen video. I know, right? I'm missing out. Am I? Am I really? I don't know about that. Anywho, we're back online here. So yes, which way would you pick to do this? If you want to predict each outcome separately, right? I want to predict the mom answers. I want to predict the dad answers. Take out the intercept. If what you want to focus on is how one outcome differs from another. So like in the previous example that we did with response time, right? We were concerned about how response times would be faster for stimuli that were more conspicuous, right? And so we wanted to know about that. That is a construct, like the effect of my manipulation on response time, and I want to know if the effect of my manipulation differs for different kinds of people, right? That lends itself to a general intercept and then a parameter that captures that difference, the effect of the manipulation as a difference, and then moderators of that difference. Here, it seems less useful to talk about how the intercepts differ between family members than it does just to say, okay, what is the intercept for each family member and what predicts each family member's outcome? So for that reason, I'm not going to show you 4 versions of the model anymore. We're going to do one. We're going to set it up without a general intercept. I'm going to write it out the long way using my own dummy codes, and the reason for that I will show you in just a minute. To foreshadow, though, the reason why you would do it the long way, to write out all the dummy codes, is to be able to have some predictors only predict certain outcomes and not others. What do I mean by that? Let me go back to the PowerPoint here in just a second. Come on, PowerPoint, go back to the other window. You can do it. There we go. We go back to this code right here. Can you see my slide 29? Okay. So look at all this typing. C, A, B, A by X, B by X. That's a lot of typing, right? And then look at this, DV, DV by X. Much less typing. But what if you wanted the effect of X not for all the DVs, but only some of them? DV by X can't do that. It puts them in for all. If you write it out, you have a custom model that you could put different predictors in for different outcomes if you needed to. So it is more typing, but it's a lot also more clear what all is in the model then. It's like nothing goes in unless you type it. There's some nice sense of control there, at least for me. All right, let me find my Word document again. I'm still getting used to this 2-monitor thing. Not a big fan, but I'm making it work. Okay, there we go. So here's our first predictive model, writing out all the intercepts myself so that I have full control over everything, and putting in one predictor. I'm looking to see whether or not attitudes differ as a function of the gender of the adult child. I already know the gender of the parents. By definition, in this study, I have moms and I have dads. but their adult child could be a boy or a girl, and that may color how conservative their gender attitudes are. So I'm putting in the kid boy is the name of the parameter, whether or not it's a girl as a default versus a boy as the one group, and that predictor, which is a family level predictor, in each of here. So in terms of the subscripts, the first subscript is for the family, and the second subscript is for the person, the individual from there. So 000102, because kid is the first predictor with respect to the person, mom is the second predictor with respect to the person, kid boy is a family level predictor. So it is the first family level predictor. So everything that pertains to kid boy has a 1 in the first subscript. And the second subscript matches which person it is the effect for. So it's 1O because O is for dad, like it was up here, and 1 is because it's the first effect of kid boy, first predictor of the family. O1 for kid matches 1-1. O2 for mom matches 1-2. So I've got 6 fixed effects in my model. I'm asking for some extra stuff, such as, is there an omnibus effect of gender? So to do that, I'm putting in 2 contrasts, kid versus mom and kid versus dad. I'm asking via the lincoms for differences in the effects of the predictor. So does gender have a bigger effect in predicting the attitude of the kid themselves versus their parents? You would expect that your own characteristic would have a bigger role in predicting your attitudes as opposed to the attitudes of your family. And here's an example of some cool extra shit that I just figured out how to do finally, and I wanted to show you. I have 3 people here, but another way to look at the same set of 3 people is a distinction between parent and child, where mom and dad are parents versus kid. So I also threw in another slope that I'm going to estimate what is the parent slope, which is the average of the mom slope and the dad slope, and I'm going to contrast that parent slope to the kid slope. And so in SAS, this is easy to do with the divisor option, and then I figured out how to trick Stata into doing it by starting the whole thing off with a 0.5. So within each of these lincoms, it has to sum to 0 to have a contrast. So it still sums to 0, but then you can have 1-1 versus -2. And by keeping the metric in 1 rather than 2, the coefficient is directly interpretable as a slope. So cool stuff, huh? Right? Maybe. But you can do anything if you know how to ask for it. I find that cool. But maybe not you guys. That's okay, though. So here's what we got. Focusing just on the fixed effects. On the whole, is there an effect of gender in predicting the attitudes of my 3 people? On the whole, no. Let's see what the effect is for each person. So here are the reference points for my model, 1 for each outcome. Given the way that the predictor is coded, adult children who are women are the 0s and men are the 1s. And so these are the expected attitudes for each type of person who has the adult child is a girl. And this is the difference in the attitudes for each person for adult children who are boys. So the fact that these coefficients are positive means that families whose adult child is a boy tend to be a little more conservative in their gender attitudes. That's what a higher score means. But the only one that's significant is right here. The gender of the child predicts their own attitude. The others, the gender of the child, does not predict the attitude of the mom or the dad. And that actually makes a lot of sense, because what happens if you have a family with more than one child? These happen to be one child from a family. There's nothing that said they couldn't have more. So just knowing whether or not this one particular individual was a man or a woman doesn't necessarily tell you about the composition of the family. So it stands to reason that the gender of the child doesn't make a difference in their parents' attitudes, because we don't know what the genders would be of their other children at a minimum. So the model directly tells me if my predictor is significant for each outcome. If I want to know if the effect is different between outcomes, I can ask for that as a linear combination. And so that's what the first three terms are. These are comparisons of these three slopes. So for kid versus mom, for the mom, the slope is significantly, actually almost marginally significantly less positive. It's a smaller effect for moms. It's a smaller effect for dads. And moms and dads' slopes are the same. So given that moms and dads' slopes are the same, rather than estimate one separately, I could lump them together. So I decided to do that. So I took those two numbers right there and averaged them to create this new term, a parent slope. The last estimate statement then compares that new parent slope to the kid slope. And that, I'll call that significant. Why not? I'm feeling generous today. P equals 0.05. So putting it together, the gender of the adult child predicts their own responses. It does not predict the responses of their parents, and it looks like it predicts their responses more than it predicts their parents. So moving forward, do I need to control for gender? Only for the gender of the child in predicting their own attitudes, not in predicting the attitudes of their parents. So even if I wanted to do less typing, I have to stick with the model in which I type it out because of that term right there. I want to have the effect of gender specifically for the kid only. All right. How are we doing, friends? Questions or any of that you want to hear again? No? You're with me? It's a lot of complexity, keeping track of what predicts what, but it's not any different than that you already know how to do. Here is another model, adding in the effect of your own education. So I have dad's education predicting his attitudes, mom's education predicting her attitudes, and kid's education predicting their attitudes. So this brings up a point of confusion in terms of setting up these sorts of studies. And I was actually on the fence as to how to explain this to you, which picture is wrong. But in the original version of this, before I decided to simplify it, I'll just go ahead and go with this. I have education in this data set in two different ways. So I have the education of each person as a separate column. That is a family level variable. So it is like the child's education is pasted throughout not only their rows, but the rows of their parents as well. And I also stacked it so that it is their own education. So the kid's education is what goes in here in predicting their attitudes, the mom's predicts hers, and the dad's predicts dad's. So in thinking about how to enter this predictor in the model, I could either do it this way directly. I have one column that is how my education predicts my outcome, or I could do it this way instead. Now the advantage of this way, having them as family level variables, is that you could have someone else's education predict your score too. Then you get into actor-partner land. How does my education predict my attitudes? How does the education of my spouse predict their attitudes? How does the education of my spouse predict my attitudes? Even though these are individual level variables, they're being treated as family level variables in the analysis because they are entered into the data set this way. That way they can predict their own scores as well as the scores of other people. So in general, I would probably set everything up this way. Individual characteristics as group level variables. That way you can have them predict not just their own individual outcomes, but those of other people in the analysis. So I have added, oh, went too far. That as education of each person predicting their outcome. Okay, does that make sense? So let's see what happened. So I've separated the new effects here with the line. The coefficients are negative, which means people who are more educated have less conservative attitudes. That is only significant, though, for dads. So if a kid has a higher education, that's not related to their own attitude. If a mom has higher education, that's not related to her own attitude. If a dad has higher education, that is related to his own attitude. And for reasons that I don't understand theoretically, but maybe you guys can enlighten me, in these sorts of studies, people insist on controlling for fathers' attitudes on a lot of things. I know, exactly, Molly. I don't like that either. But so they asked me, how would you do that? Well, if father's attitudes is entered as a family level variable, it goes through all the columns, you can have father's attitude predict each person's score. So the next model then, here are the effects of your own attitude. I'm leaving them in all as controls. And now I'm adding these terms. The effect of father's education on the child's attitude, the effect of father's education on the mom's attitude. So these are known as partner effects in the actor-partner parlance. It's someone else's predictor on my outcome. I'm also asking for some comparisons of these slopes. So there's lots of comparisons that might be of interest. Here's an example of how you might go about it. I'm asking whether dad's attitude has a stronger effect, or nope, back that up. I'm asking whether dad's education has a stronger effect on his attitude than on the attitudes of the other people in his family. And so differences in these slopes are just one minus the other. I write it out this way so that the code between SAS and Stata looks the same. But any slope that you want to know if it's different, you can just subtract one from the other in an estimate statement. And so here's what we got. So these are my education predicts my attitudes I'm controlling for the kid and the mom. And then here's the 3 effects of interests. Dad's education predicts his outcome, but dad's education does not predict the kid's outcome, and it does not predict the mom's outcome. So people from families where the dad is more educated are not different in their attitudes. other than the dad. Dad doesn't have a carryover effect, so to speak. And for many years, I've given this example in several different classes, and for many years I left it there. I was like, okay, that's the end of the handout. I'm going to write it up and turn it in. And then one year I decided to do path analysis with it, and I found out that this model actually doesn't fit very well. Lo and behold, we didn't consider mom's attitudes. Mom's attitudes matters. So that I'm just going to leave that dangling, right? We're going to revisit this example in a couple of weeks when we get to path models. But I did not know until I fit this as a path model that I was missing something. So that's actually a nice segue. You know, we have these fit statistics. You know, in REML this tracks the model for the variance specifically. In ML it tracks both. We don't know in this framework like whether we're done, so to speak, right? Like whether the model's good enough, whether we're missing anything. It's somewhat more obvious when we have this set up because you have all the variables for the different people that you could try all possible combinations, but you don't really know if the ones that you've left out should have been left out or whether they should go in. One of the advantages of fitting this exact same model in path analysis is that you get an index of what's known as model fit. Whether or not the relationships that you haven't put in should have been there. So for that reason, learning that new strategy will be very, I think, potentially helpful in very complex models where you have a lot of predictors and a lot of outcomes going on simultaneously. So I think that's a good place to stop. I went through this faster than I had planned on. That means that we get to start example 5A next time that I just finished. So, all right, questions, comments? You good? No questions? Do you feel like this is something that you guys could do? Well, you're going to find out. Homework 4 is available. I have a recommended due date of, I think, 2 weeks or something, but there's no such thing as due dates in a pandemic. This is the rest of the semester. It's a true story, as always. In terms of the content of it, you're going to have people who were trained either in how to make better pancakes or better crepes. Yeah, Jeff almost spit out his coffee. Yeah, it's another real life example. The backstory to this is that many years ago, my husband bought a crepe pan and tried to teach himself how to make crepes, and it turns out the technique for crepes is completely different than the technique for pancakes, and the two do not coincide. So in this fictitious story, we had people trained in either pancakes or crepes, and then they were asked to make both dishes. So it's a multivariate analysis, and historically people have found it hard, even though there's only 4 numbers to be compared. So we'll see if this group does better, which means I'm getting better at teaching it. And if not, then I'll let you. I'll help you as much as need be. But you get a chance to practice this with homework 4, and it is available for you to do so. Pancakes and crepes. That homework makes reference to an example that I did at the very beginning of the semester as one of the options that you could use to parameterize the model. You could either set it up as exactly what we just did for this example 4B, or you could do it like this one. This is the example 0 that I made up. That one, where each combination of group and outcome gets its own intercept. You could do it that way too. So I'll let you figure out which one you want. You want pancakes now. Well, good news, there's protein pancakes that they sell at the grocery store, and Huey likes them. So we have expanded the amount of protein in his diet finally, and he may not actually die of malnutrition after all. So we will. That remains to be seen. But protein pancakes at the grocery store, I'd recommend it. They are in a teal box. I don't remember the name of the brand. So, anywho, good for now. Ready to go? All right. Thanks for being here. Let me know if you need anything. And otherwise, have a good weekend. See you Tuesday. Bye, guys.